For a second example on hydrostatic force, let's consider this scenario. Suppose a cylindrical drum holding gasoline is submerged in water, and the radius is 2 meters, and it is submerged 6 meters deep in the water. And we need to determine the hydrostatic force from the water on the outside end of the cylinder. So we've got some cylindrical drum submerged under 6 meters of water, and the radius of this drum is 2 meters. And we need to determine what is the actual hydrostatic force on the face of that drum in the water. So that's the scenario. So we can think of the face of that drum like a plate, a circular plate that's submerged 6 meters deep in the water. And we need to come up with the integral to compute the hydrostatic force. Because if we think of slicing that little plate up into little slivers, each sliver has a slightly different area and a slightly different depth under the water. So let's start by first setting up a coordinate system that corresponds with this scenario. So if we do that, black pen. So to do that, let's go ahead. This is a circular scenario, so I'm going to go ahead and put my circular face of this drum right, call that 2, 2, negative 2, negative 2, right with the center of the circular drum at the origin it's not a perfect circle, but good enough. And then 6 feet above that, so, and again, this isn't going to be quite to scale because I'm running out of space up here, but 6 feet above that, so a distance of, I'm sorry, 6 meters. 6 meters above that is the actual water. So the top of the water is up here in my coordinate system at 8 in my coordinate system. And we're going to think about taking little slices of this face of the circular face of this drum, and we're going to be thinking about what is their area and the depth under the water in order to come up with the hydrostatic force. So just as a quick reminder of our formulas here, we're talking about force, which just the physics principles here, mass times acceleration, but mass is going to break down into, we're in water, so the density of water times volume, and acceleration is going to be gravity. And then our volume is going to break down a little bit further, and we're going to think about what is the area of a slice, area of the object, and in this scenario it's actually a slice of that circular face, and the depth. So the volume, how deep is that slice under the water? So the depth of the object. And again, we've got gravity, we've got our two constants, gravity and density. Okay, so our force boils down to rho, density, gravity, times area times depth. So kind of keeping that formula in mind every time we're doing one of these hydrostatic force calculations, and these pieces are variable in the scenario, which is why we're going to get an integral. So we need to come over here to our diagram and think about, okay, so of course gravity and density of the water are going to stay the same, but what is the area of a slice? So what is A sub I, and what is the depth of a slice? And to do that, we're going to need to consider the fact that this particular picture that we're looking at here has a circular face, and the circle based on my coordinate system can be represented as x squared plus y squared equals 4. And since the thickness of each of our slices here is actually a delta y in this coordinate system, and we can think about taking each of those slices at a particular y value, some tag. We can think of that tag as being y sub I star on the y-axis. So let's go ahead and rewrite this equation as x is a function of y. So x is actually equal to the square root of 4 minus y squared. But again, that is just for the top half. You technically have a plus and a minus. I'll go ahead and write that plus and minus here. You technically have a plus and minus the top half of the circle and the bottom half of the circle. But if we look at, I'm sorry, the right half and the left half, if we had solved for y, we would be representing the top half and the bottom half. Since we solved for x, we're actually looking at this. The positive root represents this right-hand side of the circle, and the negative would represent the left-hand side of the circle. Okay, so the area of each of those little rectangles at some little slice, the area of those rectangles is actually going to be 2 x sub I stars times delta y, or we could jump right into the fact that that's 2 times the square root of 4 minus y sub I star, wherever we've made that little slice, our representative tag, squared times delta y. And then the depth of each of those slices is, since remember we're submerged 6 meters deep, the cylindrical tank is submerged 6 meters deep in the water. So each of those slices is going to be at a depth of 8 minus y sub I star. And so the force of each little slice, the force on each slice is going to be the density of water times gravity times 2 times the square root of 4 minus y sub I star squared. I'm going to move the delta y to the end, so times the depth, which is 8 minus y sub I star times delta y. And that's what the force on each slice of the end cap of our cylindrical drum. So this is the force on each slice. But of course, and I won't show the Riemann sum, of course, if we were to add all of these up from 1 to n and then take the limit as n goes to infinity, we would end up with an integral. And before I scroll off of my picture up here, notice that we're going to be taking slices, since this entire face is submerged in the water, from -2 to 2. So we're going to take slices of that whole face from -2 to 2, so integrate from -2 to 2. So let's set up our integral. So the actual hydro force is going to be equal to the integral from -2 to 2. And we've got these 3 constants here. I'm going to go ahead and pull them out. So 2 times rho of H2O times gravity times the square root of 4 minus y squared times the quantity 8 minus y dy. And that is my integral that now I have to go in and compute. So here is the integral, and now let's take a minute and compute that integral using our integration techniques. So to compute this integral using the integration techniques, if I just first start off by pulling out the constant, 2 rho of H2O times gravity, and then I'm integrating from -2 to 2, and I'm also going to go ahead and distribute this root to both the 8 and the y. So I'm going to end up with 8 times the square root of 4 minus y squared minus y times the square root of 4 minus y squared dy. And this actually, I would have to apply 2 different integration techniques, and I want to talk about a couple options for calculating A, and we can also calculate B as well. But it does end up being 2 different integration techniques just without even looking at the bounds. The first one would be just based on its form, would be a trig sub, and the second one would be a U sub. So following kind of our protocol for how do we integrate based on form, if we do a trig sub on the first one, we're going to go ahead and on part A, the integral I've labeled A, we would go ahead and let y be equal to 2 sine of theta, where theta is between negative pi over 2 and pi over 2. And our dy in this scenario, squeeze it in here, dy is equal to 2 cosine of theta d theta. And rather than actually changing back in terms of y at the end, if I think about what my actual bounds would be here, if y equals, remember this was y equals negative 2 and y equals 2. If y equals negative 2, then theta, based on my definition now for my trig sub, theta is going to be when sine equals negative 1. So theta would be equal to negative pi over 2. And when y equals 2, my theta would be equal to pi over 2, because we'd be looking at when sine equals positive 1. So making those substitutions, and I will come back to this guy. I'm going to go ahead and put a little star, and I'm going to talk about one other way that we could think about how to integrate that particular expression. But I want to just follow through kind of our trig sub one more time. You can see a full trig sub here, and we'll go ahead and set up what the next line would be. So this would be 2 times density of water times gravity, and now we're actually going to have 2 different integrals. So this is going to be the integral from negative pi over 2 to pi over 2. We've got 8 times the square root of 4 minus 4 sine squared of theta times, and we ended up with our dy is going to be 2 cosine of theta d theta. And we can continue to simplify that guy, and this piece, I'll come back to part B in just a second. This particular piece underneath the square root, of course, becomes 4 cosine squared of theta, but we're taking the square root of that, and that becomes 2 times the absolute value of the cosine of theta. But we, of course, restricted the domain and can drop those absolute values when we made that trig sub. So this ends up being 2 rho of H2O times gravity, and we end up with an 8 times 4, so integral from negative pi over 2 to pi over 2, this ends up being 32 cosine squared of theta d theta. All right, so I'm going to pause on that for just a second. We'll finish applying some trig integrals and finish that out in just a second, a trig identity on the cosine squared. But before I get too far away from my part B up here, if I make this u sub would be the entire interior of that root. U equals 4 minus y squared, so du would be negative 2y dy, or y dy is equal to negative 1/2 du. And so making that u substitution on my integral, I end up with, and I'm going to go ahead and bring my bounds in, so I end up with a plus the integral from negative 2 to 2. Oh, you know what? Let's hold off on just 1 second. We'll change those bounds too. So if I make that substitution, it becomes a positive because it was a minus, and then the du substitution is a negative 1/2 times the square root of u du. And then if I make those substitutions, if we think about when y, separate these two, when I think about if y is equal to negative 2, well, then u is equal to 0. And when y is equal to positive 2, well, u is also equal to 0. So interestingly, this becomes an integral from 0 to 0 when I make that substitution, which allows me to just drop that part off. By the definition of the integral from a to a, this is going to be 0. So we are done with that piece of the integral. So coming back down to where we had done the trig sub, if I continue now through this trig sub, this is going to be a trig integral, and so the cosine squared is going to be 1 plus the cosine of 2 theta over 2, and continuing here, this is going to be 2, bring my constants along, and now I'm looking at the integral from negative pi over 2 to pi over 2 of 16 times 1 plus the cosine of 2 theta d theta. And integrate, let's go ahead and bring out that 32 rho H2O G and actually do the integral here. I pulled out the 16, and so now the integral is going to be theta plus sine of 2 theta over 2, evaluated from negative pi over 2 to pi over 2. When I do that calculation, I'm going to end up with 32 rho of H2O G, and I end up with pi over 2 plus 0 minus a negative pi over 2 plus 0. And so that becomes 32 rho of H2O times gravity. And that is my answer for the hydrostatic force on the end of that cylindrical drum. So I said at the very beginning, and I want to just jump back to it for just a second, that there was one other way that we could have done this integral that we might have noticed right up here. If I come back here, this particular expression, 8 times 4 minus y squared, I'll just make a little note. There is another way to compute this. There's another way to consider this. Note. And I don't think I'll go through the whole thing, but this is definitely a valid way if you wanted to consider this. When you look at the integral just from negative 2 to 2 of the square root of 4 minus y squared dy, this is actually equal to the area of 1/2 of a circle of radius 2. So if you think just in terms of areas, what we have talked about in the past, this is representing this actual area. And it turns out that the area of half of the area of a circle, that's exactly what that integral represents, which would be exactly equal to 1/2 pi times 2 squared, which ends up being 2 pi. So if we had actually done that quick little calculation and then we had plugged that back into, if we had used our integral rather than doing a trig sub, that's just an option. So I'll leave it there. So rather than doing, this is an option, rather than apply a trig sub, we could have looked at that little piece right there rather than using the trig sub. If we had used that little piece and then plugged that in rather than the trig sub, that is an option. It's very specific though, so just to be real clear, it's real specific. We had to be from negative 2 to 2 of this exact root. Okay, so in that kind of specific way, it turns out you could recognize that that's actually the area of 1/2 of a circle of radius 2. So just a couple options. Wanted to mention that here as we worked through this, but that particular hydrostatic force for the original cylindrical drum of gasoline that had been submerged under 6 meters of water can be calculated in the following way.